Hello, I'm Gillian Gehring and I want to tell you about our work on cobalt-doped zinc oxide with and without added aluminium. We find that in this case we can have polarized carriers in a sample with a substantial coercive field, which clearly has possibilities for applications. And a large coercive field can be obtained from nanoparticles of cobalt metal in zinc oxide. This is very well known. This is an example of a sample that shows this with a high coercive field at low temperatures. And not surprisingly, the zero field cooled shows a large peak at the blocking temperature. And this can be modeled in terms of the temperature dependence of the remnants, which is also measured. And the agreement is really quite good, where the two peaks are coming at essentially the same temperature. And another way in which we can verify that we have isolated nanoparticles is both the remnants and the coercivity can be fitted with micromagnetics. And finally, the off-diagonal dielectric constant which is obtained from magnetic circular dichroism, can be well fitted, assuming that all the magnetism is coming from cobalt nanoparticles. And we now compare this with a sample of zinc cobalt oxide that contains very little metallic cobalt. And in this case, the coercive field is always small, and the MCD is dominated by a peak at the band edge of zinc oxide, indicating that we have spin polarized donor states in zinc oxide, providing the bulk of the magnetization. A sample with added aluminium also has a high coercive field at low temperatures and a temperature-dependent coercive field. However, the zero field cooled plot shown here is really quite different. And also the remnants cannot be fitted using micromagnetics using the same parameters as the coercive field. And the low field susceptibilities are completely different. So we understand what's going on by analyzing the magnetic circular dichroism. The green curve here shows the experimental data, and this cannot be fitted alone to the nanoparticles, but is given by a combination of the nanoparticles and a peak at the band edge. And the two arrows indicate two energies, one where the nanoparticles are dominant, and the other one where the band edge is dominant. So we did hysteresis loops using MCD at those two energies and find we get the same coercive field. And this indicates that not only we have two types of magnetism, but that they are exchange coupled and move together under the influence of an external field.